Exportable executable PE format is the file structure used by Windows executables like exe, DLL, sys, and as usual, we'll explore the PE structure visually with PE-Bear, which is a perfect tool to parse the PEs. So let's get started. A PE file is divided into headers and sections. Let's start with the PE headers. Headers are the blueprint of Windows executable, containing all metadata needed by the OS loader to map the file into memory and execute it. To not waste too much time, let's compile a simple C++ code that saves hello world to a file called hello world. Now let's go to the executable path and run a PowerShell session and execute the file. As you can see, the file is successfully created. Now let's open PE-Bear. You can install it from this link. Let's load our PE to PE-Bear. As you can see, it quickly displays its architecture. As we said before, there are headers and sections. From PE-Bear, we can see that the first header is the DOS header. The DOS header contains information that makes the PE file compatible with old MS-DOS systems. Back in the 80s and early 90s, before Windows became popular, programs were written for MS-DOS, a simple command line operating system. The DOS header in a PE file includes a magic number, MZ, short for Marcus Bukowski, one of the creators of the DOS executable format, that tells older DOS systems, hey, this is a valid executable file. In the right, we have the structure of the DOS header, and the left, we have the PE-Bear GUI representation of this structure. As you can see, the first attribute is eMagic, which contains the magic number MZ. Then we have a bunch of other attributes, but the most important one is the ELFA-new, which tells us the offset of the int header, since this is an important header that we'll cover later in this video. The value of this header is 100, and if we go to the int header, we will see that it starts from 100. After the DOS header, we have the DOS stub, which is a small program that can run on MS-DOS. If you try to run the PE file on an MS-DOS system or an old DOS emulator, this stub gets executed. The DOS stub does not do much. As you can see here in PE-Bear, we have this little sentence that will be executed when this PE is executed in an older MS-DOS system, which is, this program cannot be run in DOS mode. This is pretty much what we need to know for now regarding the DOS header and DOS stub. Now let's talk about the int header, which holds a lot of critical information for malware analysts and reverse engineers. First of all, when a PE is loaded into memory, the operating system assigns a base address, which is the starting point of the image in the virtual address space. The file, including its headers and sections, is then mapped into memory relatively to this base address. Let me give you an example. Suppose the PE file is loaded at base hex 400,000 and the function is located at virtual address hex 401234. The RVE is calculated as RVE equals to VE minus the base address, which is hex 401234 minus hex 400,000, which gives us hex 1234. This tells us the function is hex 1234 bytes away from the start of the image in memory. Why we use RVE instead of VE? You may ask, if we already know the VE, why do we care about the RVE? The reason is the base address is not guaranteed to be fixed. It can vary at runtime due to factors like system memory layout, ACLR, address space layout randomization, a security feature that randomizes the image base address to make exploitation harder. Using RVE ensures location independence. The RVE of a function stays constant even if the VE changes at runtime. Let's assume a function has an RVE of hex 1234. Depending on where the image is loaded, if loaded at hex 400,000, the virtual address will be hex 400,000 plus hex 1234, which is hex 401234. If loaded at hex 500,000, to ACLR for example, the VE will be hex 500,000 plus hex 1234, which is hex 501234. Now in both cases, if we want to know the RVE of the function, we just take its virtual address minus the base address of the image and we get its RVE, which is the same for both cases. Now that we understand the difference between the virtual address and the relative virtual address, let's move on. The purpose of the int header is to provide metadata about the PE file, including its architecture, location of sections. If we take a look at the winint.h file located at this path, this file defines the structures used by Windows to represent PE headers and sections, such as image DOS header, image int header, image section header, and so on. We've already talked about the image DOS header, and as you can see, this is its structure. Now let's take a look at the image int header. As you can see, this is the image int header structure, which consists of three components. First, we have signature field, which identifies the file as a PA file. It's a double word, meaning it's 4 bytes long, As shown in PE Bear, this field always has a fixed value of hex 4550, which corresponds to PE in ASCII. So this header confirms that the file is a PE. Then we move on to the second element, which is the file header, also called the COF file header, with the image file header structure. We search for this structure in the same file, and as you can see, this structure has 7 elements. First, we have the machine, which describes the CPU architecture. It is declared as a word, meaning 2 bytes at offset 104. If we take a look at PE Bear, we see that it's 8664, and PE Bear is actually so cool because it gives us what that value means. In this case, it's the architecture of the CPU, which is AMD64. Then the second member is the number of sections, which holds the value 6, means that there are 6 sections in this file, and that's where we see in PE Bear. We'll explore sections in a couple of minutes. Then the third member is the timed data stamp, which is the date and time when this file was created. This is the hex value, and PE Bear convert that into a readable data time format. Next, we have the pointer to symbol table and number of symbols field. The symbol table is a data structure used by linkers, debuggers, and reverse engineering tool to map human readable names to the addresses or metadata of functions, variables, and other elements. In this case, both fields are set to 0, indicating that the symbol table is not used. Then there is the size of optional header, which specifies the size in byte of the optional header, the next header in the PE structure that we will cover. Lastly, we have the characteristics field, which describes attributes of the file. This field is a bit mask, where each bit represents a specific characteristic. In this case, the value hex 22, which breaks down as follows, which is already described in PE Bear. So we have hex 2, image file executable. The file is executable and can be run as a program. Then we have hex 20, which means that the image can handle addresses larger than 2 gigabytes for 32-bit applications. And that's it for the file header. Now let's move on to the optional header, which is part of the main NT header. The optional header, image optional header, is a key structure in portable executables used primarily in Windows executables and dynamic links libraries, DLLs. Despite its name, it's required for all executable image. It provides essential information about the binary, such as its memory layout, entry point, and operating system compatibility. The PE loader looks for specific information provided by that header to be able to load and run the executable. It's called optional because some file types like object files don't have it. However, this header is essential for image files. The header comes in 2 versions, image optional header 32 for 32-bit executables and image optional header 64 for 64-bit executable. The main difference between these versions involves data type for certain fields and the removal of the base of data field in the 64-bit version. The first element is magic, which identifies the state of the image. Is it 32 or 64-bit, overriding the machine field in the file header. If it's set to hex 10B, then it's 32-bit. If it's set to hex 20B, then it's 64-bit. If it's set to 107, then it's a ROM image. Then we have the major and the minor linker version, which is the version of the linker that is used to produce the file. Then we have size of code. This field holds the size of the code, the text section, or the sum of all the code sections if there are multiple sections. And again, we have the size of initialized data. This field holds the size of the initialized data, .data section. Then we have the size of initialized data. This field holds the size of the initialized data, the .bss section. Then we have the address of entry point, which is the relative virtual address where execution begins when the file is loaded into memory. Basically, it tells the Windows loader where to start executing code when the program runs. How does it work? When you double-click an exe, for example, Windows does this. It loads the PE file into memory at its preferred image base or a different address if ESLR is enabled. And then it looks at the address of entry point to find the starting execution point, like the main function, and then jump to that address and begin running the program. If the image base is hex 400,000 and the address of entry point is hex 1000, the first instruction runs at hex 400,000 plus hex 1000, which is hex 40,000. Now let's move on. Then we have the base of code, a double word, which is an RVA of the start of the code section. Then we have the image base, which is the preferred load address in memory, must be a multiple of 64K. Due to SLR and other memory protections, this address is often not used. Then we have the section alignment, which is describes how the sections .txt, .text, .data are aligned in RAM and when loaded. Then we have the file alignment, which describes how sections are aligned on disk inside the .exe file. Now, what's coming next is just a bunch of fields. For example, we have the major operating system version, minor operating system version, major image version, minor H version, major subsystem version, and minor subsystem version. This members of the structure specifies the major version number of the required operating system and the minor version number of the required operating system, and then the major version number of the image, the minor version number of the image, the major version number of the subsystem, and the minor version number of the subsystem respectively. Then we have Win32 version value, a reserved field that the documentation says should be set to 0. Then we have size of headers, which combines size of all headers and sections tables. Then we have checksum, used for integrity checking, especially important for drivers. Then we have subsystems. This field specifies the Windows subsystem that is required to run the image. For example, Windows GUI, console, driver. Then we have DLL characteristics, which is a flag indicating DLL properties like SLR support and so on. And then we have size of stack reserve, size of stack commit, size of heap reserve, and size of heap commit. This field specifies the size of the stack to reserve and the size of the stack to commit, and then the size of the local heap space to reserve and the size of the local heap space to commit respectively. But what is the difference between reserve and commit? Well, basically when your program starts executing, Windows reserve, for example, 1 megabyte size of stack reserve of virtual space, but it only commit 4 kilobyte size of stack commit of actual memory. And as stack grows, Windows commits more 4 kilobyte chunks up to 1 megabyte. Then we have loader flag, a reserved field that the documentation says should be set to 0. Then we have a number of RVA and sizes, which is the size of the data directory array. Then we have the data directory, which is an array of image data directory structure. Constant defines with the value 60, meaning that this array can have up to 60 image data directory entries. We will have a deep look into the image data directory in future videos. Now let's jump into sections and section headers. We are not going to spend too much time on sections since we will cover them again in future videos. But first of all, we can see that we have a header called section, which describes the sections like its RVE, size, and so on. The first section is the text section, which contains the executable code of the program. Then we have the data section, which contains initialized data like global variables with explicit initial values, static, local variables. Then we have the .bass section, which contains initialized data. And next we have the data section, contains read-only initialized data. Then we have the data contain the import tables, which lists functions imported from other DLLs, because in the next videos we're going to cover this in details. Then we have the log section, contains image reallocation information. Next we have the .rsrc, contains resources used by the program. This include images, icons, or even embedded binaries. And finally we have TLS, thread local storage, which provides storage for every executing thread of the program. In future videos, we're going to cover those sections in more details because we're going to try to parse them. So see you in the next video.